Good afternoon. Assalamu alaikum to all. Okay, today we have the second part of the talk on fuzzy logic, which is on the fuzzy logic controller. Basically, we look at the fuzzy logic controller concepts, design methodology, and some examples how we're going to design using MATLAB. Okay. Basically, the fuzzy logic control concept again coming from the fuzzy rule base. For example, in this case, operating a boiler and trying to control the water from the boiler feed tank. So it's how the operator is going to think. If the level is high, then the valve should be closed. If the level is okay, good, I call it good, okay, linguistic uh, values here, good, then the valve is half open. If the level is low, then the valve is open. So these are the fuzzy logics, linguistics, and rules that we the normal human being thing, and this is how we're going to design our fuzzy logic system. Okay, the advantage of fuzzy logic is that basically it's comparatively easier than developing the model base where you have to get models and all that. It's robust in general, more robust than PID because of the capability to cover huge range of operating conditions in knowledge system, as we mentioned before. Can be customized to different areas and different systems. Basically emulate the human deductive thinking is what we've seen before, the example in controlling the boiler, designed to emulate human deductive thinking and to infer conclusion from what we already know. Reliability, more reliable than conventional in non-linear system normally. Is generally more efficient when applied in control system in general, okay, not specifically but in general. Okay, disadvantages, well, it requires lots of data. You need data, historical data, to be able to design your fuzzy rule base, or you need human expertise. The accuracy of the system depends on the knowledge and the expertise of the human beings in developing again the rule base. And of course, these rules must be updated from time to time. Okay. Looking at the control system, as we've seen before in your process control class, we have the controller, final controller, process, and measurement device. So basically, the same loop applies, except that now the controller would be the AI or fuzzy logic controller, and the others should be similar in terms of the final control process, measurement device, but we may have more measurement than just one. Structure may slightly change, the controller will change. That defines the advanced control strategy. So why this is called advanced? Because of this issue of the difference in terms of structure and the controller itself. Okay. For fuzzy logic controller, basically we have this component we mentioned before in the introduction class. We have the fuzzifier, transform the input data into fuzzy sets, the inference mechanism, and the fuzzy rule base in one part of the fuzzy logic controller. And finally, we get a few rules that fire, then we come up with the aggregation part where you come up with a fixed value from the defuzzifier. So the defuzzifier converts the fuzzy to crisp, non-fuzzy or real data. Two methods, but there are other methods in doing so. Four elements in the fuzzy logic controller. One is the rule base, premise, then consequent, which contains the logic quantification of the expert's linguistic description of how to achieve good control. The inference mechanism emulate the decision making by interpreting and applying the knowledge about how best to control the plant. The fuzzification process that converts the inputs into the antecedents fuzzy set that can use to activate and apply rules, and the defuzzification converts the action of the inference mechanism into actual inputs for the process. So these are the four elements that we have mentioned before. Fuzzy logic design methodology. First of all is to choose the fuzzy controller inputs and outputs, and then putting the control knowledge into the rule base, then the fuzzy quantification of the knowledge, then matching which rules to use, and then determining the conclusions, and from the many different different conclusions or different rules fired, and finally converting the decision into actual action into the real plan. So these are the methodology that we have to follow. Basically, the first one is the FLC design methodology is choosing the fuzzy controller input and output. Okay, that from the expert of your knowledge will tell us which should be used as the input. So there are many choice, but normally in some process, first one is the error, set point minus the actual, and the change in the error is also important. So this relate to the process input values. Okay, and then the output depends on what you're trying to manipulate, and normally relate to the finite element, how we can manipulate the process variable. In this case, like height. So the output could be the valve opening and valve closing, or CV percentage, we call. Okay, in choosing the fuzzy control inputs and output, we define the linguistic variable for each of the input output. Okay, for error described as ET, and change in error described as the change in error. Okay, these are the variables, and the output, the valve rate, defined as the change in the valve opening. And for each of them, we define its linguistic members. Okay, or linguistic members, or sometimes called linguistic values. For input 1, we define the linguistic variable error into different linguistic members. For example, negative large, small large, 0, positive small, and positive large, 5 members. For the change in error, as input 2, we define 3 members, negative, 0, and positive. And for the output, as the valve rate, we define another few members here: close fast, close slow, no change, open slow, and open fast. So 5 other members for the output value. So this is the fuzzy membership linguistic variables and fuzzy linguistic members. And then next we go to the fuzzy membership. Before that, we would like to put them into rule base. Suppose that the human knows certain function of the plant in some natural language, so we can set up this what you call matrix sort of thing. Yeah, the FAM in terms of numbers, change in errors. These are the numbers: the negative, 0, positive. The errors in the negative, 0, positive. You can have more. You can have more. It's up to us. And the output is the force U. So these numbers we would like to change. These are the range in terms of the values, but we would like to change them into the linguistic value we've been talking about. But before that, we also have to decide these members which membership function they lie in. So if you like to use a triangular, then you have to decide the triangular, what sort of triangular, give the details of the beginning, the middle, the end, and so on. You want to use a trapezoidal, then you decide the trapezoidal definition or specification. You want to use a Gaussian, you decide the Gaussian, and so on. So there are a few more, but these are the 3 common membership functions that we define for the linguistic. And finally, we want to mesh. Just now, as we said before, we want to mesh the rules. Okay, once we have the input values. For example, if we have an input E equals 0 and change in E equals 0.3, then we have 2 rules are fired here. Looking at this, okay, error 0 and change in error is 0 and error is 0. Then if the one rule is fired, where change error is 0, then this rule is, then we can use this rule here, basically 0 here. The force is 0. Another rule, if error is 0, change in error is positive small, is 1, then the force is negative small. Another rule is being fired. So, okay, so these are the rules that we have fired based on the input that comes in, and in terms of the linguistic variables that we have chosen, and in terms of the rules that we have given. Okay, so in this case just now, when we have the C0.3, okay, so as I said, we can fire 2 rules. One is with the 0 membership function, and one is the positive small membership function. So this is the mu is the what we call the degree of membership function, the degree of membership, now from 0 to 1. So when we fire the degree of membership for the 0.3 and 0, so we will get a value of 0.25 and 1 for the 0 part. And when we use the rules n, normally we choose the minimum of them. Take the minimum of those two, which is 0.25. The other membership function for the other rules is the we fire the 0.75 with the 0, 1. And again, using the n rules, we take the minimum of them, and which is 0.75. So two rules are fired here. One with the 0 membership function, which is 0.25 degree of membership, and another rule using the negative small membership function, the degree of membership is 0.75. So we have two rules fired. So we have to aggregate them to get the final output. One is the negative small membership function, one is the 0 membership function, which is 0.75 and 0.25. So we aggregate them to decide one output. We have to come out with one output with a final one output value. So we have to go through this, converting the decision into action using the defalsification method. We can use different methods, center of area, mean or maximum, and so on, right, method and so on. Normally we use the center of area or the centroid or center of gravity method to decide the different rules fired, and we want to decide what is the final. So we will use that defalsification method. Okay. We'll take an example now. If we use the Cribs input E equals to minus 0.5 and the Cribs input for change of error is 0.6. So we have two linguistic variables used. We call it A1, or we call it in this case, the linguistic membership is in terms of x1 or y1. Okay, linguistic values in terms of x1 or y1, and the membership function is a1 or a2 or a3 for the input x1. For y1, membership function is a b1 or b2, trapezoidal b1 or trapezoidal b2. So these are the two different categories of inputs. So the membership function for the a1 will be 0.5, and the membership function for B1, B1 would be 0.1. The second one, membership function for A2 will be 0.2, and the membership function for B2 will be 0.7. So these are the inputs that has been converted into fuzzy linguistic variables and their values. And we have the rules. Okay, we already set the rules that if E is A3 or C is B1, then we get Z is C1. C1 is the membership function of the output. The other rule, if E is A2 and C is B2, B2 are the membership functions for the inputs, and we use N, then Z is the C2 membership function of the output. And rule 3, if E is A1, then Z is C3. So this is the inference mechanism combined with the fuzzy rule base to come up with a degree of membership and to decide which rules to be followed. So just now we have said, okay, we have if A3 is fired and B1 is fired, then we use the OR value, okay, which OR means normally is the maximum of the value is 0.1. So C1 is fired with 0.1 degree of membership. If X is A3 or CE is B1, then Z is C1, which degree of membership 0.1. For the other rules, if X is A2, okay, triangular, and C is B2, this trapezoidal sort of shape. So we get this is a membership degree of membership 0.2. This is degree of membership 0.7. If N, normally we take the minimum, so the minimum of this three is 0.2. So it's a 0.2 degree of membership for the output at C2 membership function. C2 is the trapezoidal membership function. The third rule, X is A1.5, we say Z is C3. This C3 trapezoidal rule, which is a value which is also 0.5. So we have, based on this linguistic membership variables rules, we have fired 3 rules are fired. C1 with degree of membership 0.1, Z C2 with degree of membership 0.2, C3 with degree of membership 0.5. So we combine them, aggregate them basically to get the final rules output combined together, and then finally we have to use the differentiation method. You get just one output. You want only one output at the end. To use the differential way, okay, whether we want to use center of area or center of gravity or mean or maximum, whatever. So we can just what do you call implement method we want. In this case, we use the center of gravity, which is given by this basically the area of the different parts, okay, plus this part, okay, divided by the degree of membership for each of the different parts, 0.1, 0.2, and so on. So this is center way of calculating center of gravity. So the final value we get is 67.4, and this is the Cripps value or the definite value or the real value that has been differentified. The whole system has differentified. This is the value that is going to the output. That is one that is applied. So this the whole steps of fuzzy logic controller, in this case controller, or any others that you may use if not a controller. That's the way how fuzzy logic is going to work. But in that case, it was a controller because we talk about errors and so on. And basically, we're going to use it. We'll use the MATLAB interface and choose the fuzzy inference system editor, the membership averaging editor, the rule editor, and surface viewer. As I mentioned before, these are the different parts of the MATLAB toolbox for fuzzy logic that we can use to design our system and for the letter system. Yeah, so we can define the input, output, and so on. Decide the linguistic variables and form the fuzzy associative matrix. Okay, in this case we have the linguistic variables for error and rate. Okay, and the values such as increase, no rate, decrease, low, good, high for the inputs, and the output as open, mid open, and so on. So it depends on how you define the linguistic variables and their values. Values in terms of fuzzy values, yeah, open, mid close, and so on. Just now we talked about uh, tall, short, fast, loud. Okay, in terms of the linguistic variable height and so on. So these are the table we can use. These are the fuzzy rules we use, and then all the other steps that we have mentioned before in the fuzzy logic toolbox. And basically, this is sort of specification that we're going to come up with using the Mamdani method. Okay, Mamdani method is what we have been studying. Mamdani method. The other method is the Sugano method. It's just the difference is in the differentiation part, where the output is a function of all the different rules fired. Function of the first rule, function of second rule, and plus function rule to get out the Sugano output. But Mamdani output is in what we have studied before. Different rules fired, aggregate them, get the implement the differential and get the one method. So it doesn't matter which method you use, but in toolbox, most of the time we can easily use this Mamdani because it's so very user friendly. And so we decide the end method, what sort of method we use, the OR method, or so on, what are the inputs, and what are the range of the inputs, what the membership function, input 2, what is the range, and what is the membership function, output, what is the range, what is the membership function, what is the name, and so on. So define this as specification into the MATLAB toolbox for fuzzy logic, okay, and then we can easily design any controller, any system we want. Yeah, as long as we know the basics, as I said, the way we choose the variables, the output, the range, the membership functions, all makes a difference. Okay, whether you want the membership functions, a lot of linguistic variables, membership functions to overlap or not, all that makes a difference in terms of the final output result. So you can use it like that blindly, but it will not be robust if you use it blindly. You have the basic understanding and knowledge of how to use it, you'll get a very good robust fuzzy logic, just like for the neural network. Okay, so this is the final sort of fuzzy logic controller you can call for, and that's all. Okay, thank you very much for your time, and we will next give you the question for the tutorial where you can use manually to design your fuzzy logic output part. Just the output part we can do manually. Other than that, it will be very, very difficult to do all the steps manually, but mainly the last part, it's much easier to do manually. Okay, thank you very much. Assalamu alaikum.